All right, we're going to start this unit by learning about heating and cooling curves and the calculations that go with them. This is something that we cover in regular chem during the first unit, so hopefully we need to just kind of get the rest off and then we can be rolling with these. All right, I'm going to first go through all of the units that we're going to see in the calculations for heating and cooling curves. So the first is energy or heat, which will be measured in joules or kilojoules, really joules for us, but throughout this unit, you'll see joules and kilojoules. I need you to know that 1 kilojoule is equal to 1,000 joules. Not so much with heat calculations, but in other problems this unit, you'll have to go back and forth between those units. And in these equations, it's going to be Q, and that's usually what you're solving for is Q, the heat or the energy required. We'll need to use mass, which is going to be in grams, and then temperature, which will be Celsius. And don't forget the triangle in calculations or equations means change in. So delta T is talking about the change in temperature. In these calculations, you're going to see something called specific heat, which is the amount of energy necessary to raise the temperature of 1 gram by 1 degree Celsius. So if I have a substance and I want to heat 1 gram of it up 1 degree, we're going to use the specific heat, and we'll see that capital C in several of the equations. Every substance has its own specific heat value for each state of matter. So these have to be given to you. We're going to focus on water today, so I already gave you the 3 values for water. I put both the heat of fusion and the heat of vaporization on the same slide because they're very similar. So heat of fusion is how much energy is required for 1 gram of a substance to be converted from a solid to a liquid or a liquid to a solid. And the heat of vaporization, same idea. How much energy does it take to convert 1 gram of something from its liquid state to its gas state or gas to liquid? So we'll use those in 2 of the equations for our phase changes. And again, every substance has its own heat of fusion or heat of vaporization value. We're going to focus on water, but these would be given to you in a problem. Okay, so this graph is a heating curve, and this is the full graph starting at a very, very cold solid ice cube and all the way up to a very hot water vapor. So this is basically as big as this graph can get. So right now, we are starting at negative 20 degrees Celsius. So we are at the solid, let me grab my pen. We are at the solid state. Okay, so we have solid, we're doing water for this one, so solid ice cubes. As we go, we are adding, if you look at the x-axis, we're adding heat or thermal energy at a consistent rate. So we're adding heat, and what that causes these blue particles to do is they start to warm up, which means their kinetic energy is increasing. So those particles are vibrating faster and faster, and their temperature rises. At some point, we're going to hit a magic number for water, which is 0 degrees Celsius. At this point, we're still, you can see the graph is still kind of moving over towards the right. We're adding heat or thermal energy, but now that energy is being used to rip those molecules away. So instead of making those particles move faster, it's being used to change the position of the particles, which is potential energy. So this slanted solid line, we are changing the kinetic energy of the particles. This flat line, when we're melting, we are changing the potential energy. So notice that flat line, no temperature is changing when an ice cube is melting. I think that's super interesting, one, because I'm a giant nerd, but also it really has brought up many arguments in my family because my dad's like the cooler guy. So anytime we go to a Bears game, he always packs the cooler and he's always stressed that there's not enough ice in the cooler. What my dad doesn't understand is as long as there's ice, any piece of solid in the cooler, it's going to stay at 0 degrees Celsius until the last ice cube melts. So if you're ever in charge of putting a cooler together, you know that the temperature of the water in the cooler is going to be 0 degrees as long as there's still some ice in there. Does it have to be all solid ice? No, but it's going to stay at 0 until the last ice cube melts, and then when it's all liquid, that's when it starts to become warmer water. So then we go to our slanted line. Now we have liquid particles. Notice there's a little more spacing in those guys. And we're adding heat, which causes those particles to move faster and faster and faster. We're increasing our kinetic energy until we hit the 100-degree mark. So again, 100 degrees Celsius is an important temperature for water because that's when boiling happens, or if we're going the other direction, condensing will happen. So now we're still putting in energy as we kind of tick our way across, but that energy is being used to move those particles away from each other, increasing the potential, or changing, I should say, the potential energy of those particles, depending on what direction you're going. And then last but not least, after all of that liquid water is water vapor. We can heat it up some more if you have an apparatus to do that. So we make those particles move faster, faster, faster. We increase the kinetic energy until I put 160 degrees Celsius on here, but until the problem tells you to stop. These heating curves can be used to represent phase changes going in either directions, heating up, cooling down, for any substance that you can heat up or cool down enough to go through a phase change. Water is going to be what we're going to use, but just know we can do this with any substance. It might just change then the melting point, 0, and the boiling point, 100, if it's not water. Every substance will have its own melting point and boiling point. One cool thing with these graphs then, if you have a problem and you kind of sketch out the graph of what's happening to the particles, you can apply a calculation to each little line segment. So the slanted line calculation, so those are the lines that kind of had the angle, solid, liquid, and gas. What we're doing there, just to review, we're adding energy and it's causing the particles to move faster and faster. That's why the temperature is rising, and that changes the kinetic energy of the particles. Well, we're going to use this Q equals M times C times delta T to calculate the energy for those slanted line segments. So I call it MCAT, but it's mass times the specific heat times the change in temperature. And then the flat lines, that's where our phase changes. Oops, that's not really flat. Pretend that's flat. Our flat line calculations, that's where the phase changes are occurring, melting, freezing, boiling, condensing. We're putting in energy, but it's being used to move the position or rip those particles away from each other or bring them closer together if we're going the other way. Temperature is not changing here, but we change the potential energy, the position energy. So to solve for the amount of energy for those phase change lines, we're going to use Q, which is our energy, equals H times the mass. So I'll just go through these really quick. If we're starting at -20 going to 0, that red line, we're going to use Q equals MCAT. So we're solving for Q. The unit will be joules. We take the mass that's given in the problem times the specific heat of solid water, again, that's provided for you in the problem, and we're going to multiply that by the temperature change for that line segment. So in this case, times 20, because we went from -20 to 0. Our first flat line here, this guy is showing our melting phase change. So we're going to take the heat of fusion times the mass given in the problem. Remember, heat of fusion is how much energy it takes to get 1 gram of water to go through this phase change. We could potentially have more or less than 1 gram. So it's a simple calculation. Take that heat of fusion value times the mass to figure out, well, with the mass given in the problem, how much heat or energy is required. All right, we got another slanted line. This is where we're heating up, moving the liquid water particles faster. So we're solving for Q times by the same mass of water. Remember, mass is always conserved. We're not losing or gaining any mass. We're going to multiply it by the specific heat of liquid water, so a new number, but it will be given to you, and then times the temperature change of that line. So in this one, we're going from 0 all the way to 100, so it'll be a temperature change of 100 degrees Celsius. Then we got our boiling line, so we're going to take the heat of vaporization of water, which is a given value. That's the number related to boiling 1 gram of water, so we'll multiply that by the mass given in the problem. All right, last but not least, we have this gaseous water. Hopefully you see the pattern, slanted line. We're going to use Q equals MCAT. So to find the heat, we're going to take the mass times the specific heat of water when it's a gas, times the temperature change. So for this graph, it looks like we're stopping at 160. So the temperature change would be from 100 to 160. So our temperature change would be 60 degrees Celsius. So here's the full kind of picture, all of the different lines with the calculations. Hopefully you see the pattern. Just know I could do this graph kind of as a mirror image or a reverse, where we started hot and cooled it down. If we were going that way down the graph, that would give us in exothermic. So at the end, when you get your answer, we would put a negative sign on the Q value. So I solve it the same no matter what direction. I always get a positive Q, but then I know if I'm cooling it down, that's going to release energy, so that's a negative Q. So I just slap a negative on there. And then if we're going the way I kind of talked about and explained where we heat it up, that's going to be endothermic. We're putting in energy, so our Q value at the end will be positive. All right, so here's a typical problem. It says 500 grams of ice in a cooler at the Chicago Bears tailgate starts at -5. How much energy is absorbed when the ice completely melts? So I think the hardest part for kids is, where do I start these problems? A full problem will go from a negative temperature to a temperature above 100. This one does not. So it's sometimes challenging to figure out, where should we even start? Personally, I start with the graph, because if I draw the graph and know where I'm starting and where I'm ending, I know exactly how many calculations this problem requires, because not all of them will require all 5 steps. When making the graph, I start by putting only the important temperatures. Important temperatures will be starting temp, ending temp, and then 0 and 100 degrees Celsius for water, and this is ice, so it's water. So I put the starting temp of 5, and then I put 0 because I know that at 0 degrees Celsius, solid ice will melt. It doesn't say anything else that we're heating up the liquid or anything like that. They just want completely melted. So I think we'll be good with those 2 temps on my axes. I got my first line segment. I know I'm going to take those ice cubes, put in energy as we go, and what that's going to do is it's going to cause the kinetic energy of the particles to rise until we hit 0. When we hit 0 degrees, that's where my melting, my phase change is going to happen. So I'm still putting in energy, but now it's being used to rip those molecules away, change the potential energy of the molecules, not the temperature or the kinetic energy. I know that after that 0 degrees Celsius, the problem doesn't talk about heating up a liquid, so I'm done. This is only going to be a 2 calculation problem, because we're starting at a negative and we want to completely melt the liquid. So that's that green flat line. So I put the calculations that go with each segment on the graph, just to help me. You don't have to do that. So I called that red line segment A. It's a slanted line, so we're going to use that Q equals MCAT equation. So we're going to take the mass, which is 500 grams, that was given to us in the problem, times the specific heat of water when it's a solid. That will be given to you in the problem. I didn't put it on this slide because you had it a couple slides ago. And the temperature change for this line segment is from -5 to 0, so we changed 5 degrees. Multiply those guys together. That Q value, 5,250, is the amount of energy it takes to heat up the ice from -5 to 0. Now I'm going to plug and chug for that line segment B. So this is where we're melting. We're going to take the heat of fusion of water times the mass. So the heat of fusion of water is 334 joules per gram, again, given to you on an earlier slide. And the mass is still 500 grams. So multiply those, we get the Q value of 167,000 joules. That's the amount of energy required to melt all of the ice in the cooler, to completely melt it. So we got how much energy it takes to heat it from -5 to 0. We got how much energy it takes to fully melt that 0 degrees cooler. And last but not least, if we're looking for the total energy, we have to add those 2 answers together. So 5,250 plus 167,000 joules will give me 172,250 joules as my final answer. And here's just some helpful values for you guys, so it's all in one place. This is just for water. I would have to give you the values for any other substance. Truthfully, when we do practice problems, I expect you to look at this page for water. I'm not going to put in every single problem, but if I ever give you a phase change calculation for a different substance that's not water, I will give you those values for specific heat, for heat of fusion, heat of vaporization, boiling point, and freezing point. I will give those to you in the problem. And oh my gosh, what a hot mess express. Can we call this one freezing and this one boiling? All right, no judgment.